Hubble's law, V equals hd. Let's apply that and work out where it comes from. So it turns out, if you plot the distance to galaxies against their speed, how fast they're going, according to redshift, so calculating from redshift, it turns out they make a pattern a bit like this. Something like this. So at the beginning there's not much of a pattern here, but the further away we get, the more they tend to fall along this kind of a line. So V equals hd, V is proportional to d. So that's interesting. That tells us that the further away a distant galaxy is, the faster it's moving from us. So it's not just that the universe is expanding, it's that it's expanding with a certain pattern. So the further away it is, the faster it's going, which does mean that if you play it backwards, well, there's a lot of uncertainty here, play it backwards, then it will get to zero size, i.e. the Big Bang, or at least something very close to that, something very close to the pure Big Bang model. So we can find the gradient of this, which is h. H naught, strictly speaking, it's the Hubble constant right now. It could have changed, it could have been different in the past. But it turns out that it is about 70. That's a strange unit. Kilometers per second per megaparsec. So generally you would measure this in kilometers per second, and here megaparsecs. The pattern isn't that strong on close galaxies. Even close galaxies like Andromeda, they're not far enough away to count for this. So it's a very much big picture. It's a cosmological model. So 70 kilometers per megaparsec. Let's do a quick example. Suppose we found that something was moving at, let's say, 1% of the speed of light. How far away is it? Well, let's use this. Got to be careful with the units. So 0.01c, I want that in kilometers per second. So that's 3 times 10 to the 8, but I'm going to change it to 5, because that's kilometers per second, times 0.01. So 3,000 kilometers per second. So the distance is V over h naught. So 3,000 over 70, which is about 43 megaparsecs. Got to be careful, you've got to use kilometers per second and megaparsecs, or that number won't work. So that's how far away it is. Even that's not that distant a galaxy, to be honest, so the rule wouldn't apply that well. Now, one more thing about this. Let's look at this unit here, 70 kilometers per second per megaparsec. So that's kilometers per second per megaparsec. We've got kilometers divided by megaparsecs here. Of course, that's a distance over a distance, so they should cancel and give us a number in per seconds. But that's tricky. We need to cancel kilometers and megaparsecs. So if you look it up, a megaparsec is 3.1 times 10 to the 19 kilometers. So if I divide that by that, so 70 over 3.1 times 10 to the 19, then the distances should cancel. And I get about 2.26 times 10 to the negative 18 per second. That's the fraction by which all the distances grow every second. So so the scale factor is that much more every second. Doesn't mean a lot to us just now per second, like while I'm making this video. Let's convert it to per years. So there's about 3.2 times 10 to the 7 seconds in a year. So multiply those. And this is still Hubble's constant, of course. So Hubble's constant is 7.2 times 10 to the negative 11 per year, or 7.2 times 10 to the negative 2 per billion years. So that's about 0.7%. We're saying the universe gets bigger by about 0.7% every billion years. No, sorry, 7%. 7% every billion years. Yeah, 7.2% every billion years. Here's the surprising thing. If you take 1 over that, it comes out to be 13.8 billion years, which is one way we can work out the age of the universe, as you would expect. That's an upper limit, and I have asked this question. That's an upper limit, saying the universe is no older than that using this model, because it could have been faster in the past. So because of gravity, we would expect the universe to have slowed down. So that's an upper limit for the age of the universe there, 13.8 billion years.